A black hole can leave a visible wake years after swallowing a star. That wake can tell the whole story, even if no one watched. Reconstructing unseen cosmic events means using indirect clues to infer a past sequence. This matters because most dramatic acts are too brief or too far away to watch directly. Astronomers read timing, color, motion, and particle signals from many instruments. They compare those clues to physics models and to large simulations to reduce ambiguity. A fading optical glow with radio shells expanding over 3 months signals a supernova. Observers then measure velocities and composition to estimate explosion energy and progenitor mass. So the immediate payoff is this: indirect clues reveal detailed cosmic stories. A faint ultraviolet halo blooms along a distant galaxy arm tonight. That halo is radiation from particles heated by fast shocks. This matters because wavelengths record different physical processes and timescales. Telescopes split light into spectra, then measure line strengths and Doppler shifts to infer physical conditions. Observers infer temperature, density, and velocity from line ratios and profiles. A Type Ia supernova peaks in optical brightness near 20 days after explosion. Ultraviolet lines can reveal interaction with a companion star several weeks later. So precise multi-wavelength light measurements convert photons into event timelines. A quickly expanding shell of gas looks like fractured glass in space. That debris is a remnant, preserving geometry and composition from the blast. Remnants matter because they record asymmetries and mixing long after explosions. Shock heating excites atoms, which emit characteristic spectral lines we can measure. Doppler shifts map velocities, revealing jets, clumps, and three-dimensional motion. Cassiopeia A has iron pockets moving at 5,000 kilometers per second, revealing strong asymmetry. Combining element maps with measured speeds yields estimates of explosion energy and progenitor mass. Thus, debris patterns act as time capsules for unseen blasts. A faint web of filaments threads between galaxy clusters across huge distances. Those filaments trace where matter concentrates on cosmic scales. This matters because environment shapes where events start and how their debris evolves. Astronomers use surveys and weak gravitational lensing to infer invisible mass distributions. Simulations predict filament geometry, which observers test against survey maps statistically. A cluster collision can show a 200 kiloparsec offset between gas and dark matter. That offset reveals impact geometry and relative velocities of the colliding masses. So cosmic maps give essential context for interpreting indirect clues. A lab bristles with detectors, their cables snaking like roots under lights. Measurement means turning raw detector counts into calibrated physical signals. Precision matters because noise can imitate rare cosmic signatures and mislead us. Teams calibrate sensors, subtract backgrounds, and validate signals against controls. Cross-correlation across observatories increases confidence and narrows sky localization. A neutrino within 0.5 degrees of a blazar flare increased the source probability significantly. Adding electromagnetic follow-up strengthened the identification into a robust claim. In short, careful measurement turns tiny blips into reliable astrophysical evidence. A single gamma-ray flash can outshine an entire galaxy briefly, then vanish. These flashes are gamma-ray bursts, extreme releases of high-energy photons. They matter because bursts mark the universe's most violent explosions and jets. Satellites detect the initial flash, and ground telescopes chase the afterglow across bands. Comparing spectra and decay rates distinguishes mergers from collapsing stars. The 2017 neutron star merger produced gravitational waves and a short gamma burst. Follow-up optical observations revealed a kilonova rich in heavy elements. Therefore, matching quick flashes with broad follow-up reveals event types. Gravity waves sweep through spacetime like distant thunder rolling over fields. A gravitational wave is a tiny strain in spacetime from moving masses. They matter because waves trace bulk motion independently of light emission. Interferometers compare laser phases across long arms to detect minute-length changes. Multiple detectors triangulate positions, and waveform shapes reveal masses and spins. The 2015 black hole merger produced a chirp that matched numerical relativity models. From that match, scientists estimated precise masses and merger rates for the population. Thus, gravitational waves provide a direct, independent forensic line for dynamics. A detective spreads fingerprints across a table, searching for a single pattern. Astronomers combine messengers to build one coherent event narrative. This matters because individual signals are often ambiguous and degenerate. Teams run forward models that predict light curves, spectra, particles, and waveforms for candidate scenarios. They fit those models jointly and use Bayesian comparison to weigh competing hypotheses. G170,817 matched a gravitational waveform, a short gamma burst, and kilonova light. Those joint clues confirmed heavy element synthesis in neutron star mergers. So multi-messenger synthesis yields stronger and more detailed reconstructions. If you remember one thing, indirect clues can tell detailed cosmic stories. If you enjoyed this, consider subscribing for more cosmic deep dives.